Okay. A very warm good afternoon to all of you, and welcome to the 5 days faculty development program on innovative research and development trends in electronics and communication engineering, organized by Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management, Greater Noida. I, Dr. Asa Sharma, on behalf of EC Department, welcomes Galaxy of Intellectuals, Your Excellency, Chief Guest of the Day, respected HOD Sir, Director Sir, HODs of all other department, faculty members, and dear participants. Thank you for taking time out and being here today. Today we are grateful to, sorry, we are very grateful to have Dr. Dushyant Sharma as our chief guest of today. The talk, the agenda of the talk is understanding real-time simulations applications for power engineering. Before that, we will have a quick go of briefing the Department of Electronics and Communication here at GL Bajaj for an overview so that you can have an idea about us. So I'm just sharing my screen. Is my screen visible? Please, anyone confirm?
Yes, yes.
Yes.
Okay. So this is the slides which we have prepared so that we can give an idea about who we are. So first of all, GL Bajaj Institute of Technology and Management. It is a prestigious institute under the banner of Rajiv Memorial Academic Welfare Society. And the institute is approved by AICT, MHRD, and is affiliated to AKTU University. We are quality-driven educational institute in Greater Noida, Delhi NCR region, and are one of the best engineering and management college in Uttar Pradesh, that is North India. About the department, we are NBA accredited, and the vision of the department is to become a department of repute and prepare globally competent and socially responsible professionals with holistic knowledge and technical skills. We offer BTech courses, which is approved by AICT and is affiliated to AKTU University. And this department has established right from the inception of the institute, that is since 2005, and we are making all the best of its efforts to meet the objective of achieving technical excellence in the areas of electronics and communication engineering. The highlights of the department is since its inception from 2005, we have 60 seats. We started with 60 seats, and now it has been increasing from 120 seats to 180 seats in 2019. And we are delivering the best results. In Uttar Pradesh, the first year result has been the topmost, and our research has been very much prominent. We have 5 research groups here, and our faculties and students are filing up almost, there are 20 plus patents filed and published, as well as 300 plus research articles are done in repute international journals. We have 6 advanced laboratories along with 11 laboratories for our students, and we our students are getting grants and awards. Around approximately 15 lakhs Indian rupees has been granted to them in awards. These are the highlights which we focus on 360 degree on the student development, where we are working on state of art laboratories. We have highly qualified faculty. We organize annually international conference medcom, which is going to recently happen in October, which is being sponsored by Springer. And we are working on the research innovations and incubation supports, organizing international and national webinars, calling up guest lectures, uh, eminent personalities from IITs as well as industries. And we are conducting extracurricular activities for the overall development of the student. We focus on the placements and alumni interactions, providing them. The target has always been the 100% placements to all the students. We also organize industrial visits at repute organizations. We have at the department NPTEL local chapter, IC, EIT GL Bajaj student chapter, IEEE GL Bajaj student chapter, international journal, as well as department newsletter. These are the best brains to mentor the bright minds, all the faculties which are here at the GL Bajar Department of Electronics and Communication. These are the advanced laboratories to make the students industry ready. We have Cisco Networking Academy, Technology Incubation and Development Center, and Center of Excellences. These are some glimpses of our student achievements, where one of our student, Kajal Srivastav, her project was selected among the only 5 projects selected from Pan India to be showcased in front of Prime Minister Shri Narendra Modi and Prime Minister of Israel, Mr. Benjamin Netanyahu, in iCreate 2018. And also our students are actively participating on international as well as national forums, and they have won many accolades, like in Anveshna they have won. These are other glimpses where they have won in startup awards, 2 of our students. They also participate actively on divisional innovation exhibition. Their project was awarded with second prize in Best Waste Composer. Then they also actively participate in technovation hackathons, and also leading global forums like Women Economic Forum, where one of our students was representing as the young innovator, which is creating a better world for all, and was a delegate there. We have also signed MOU with ALTTC, BSNL Ghaziabad. Our students are placed, we always are focused on providing 100% placement. This year currently we have the record breaking placement of 92%, where the highest package was of 18.2 lakhs, and they were placed in leading institute, that is a leading organization, Cisco. And these are the top recruiters for EC 2021 batch, which is a big highlight for our department. Our students are also very creative and innovative, and they have established their startups. They work upon them. So this is the EC third year student who has placed his startup. He's a budding entrepreneur. We also organize for our faculty as well as students we webinars, not only nationally but internationally. So renowned persons are invited, and we always get enlightened by such sessions. These are the industrial visits where we take two students to leading organizations like ST Microelectronics, ALTTC, Ghaziabad, Electronica India, Uniconverge Technologies, Ministry of Electronics and Information Technology. These are some of the notable alumni which are being placed in reputed places in Air Force, Army, Ministry, Government of India, ISRO, and they are part of now GLB family. So that's all about the department. And if anyone wants to reach us, you can drop your query here at this address. We will be happy to answer it. So this calls all the about the department. Now, not taking much of time, I would like to invite HOD sir to enlighten us with some of his kind words, and welcome our speaker. Sir, your mic is muted, sir.
Thank you very much. Respected guest of the day, Dr. Dushyant Sharma ji, all participants, HODs, good afternoon to all of you. I am very glad to see that my speaker has joined before time, not in time, before time, and that is called the sincerity. And from where he is going to deliver the speech, that is USA. Just imagine, he is sitting at 4 o'clock morning, but people in India still they are late. Sir, I am very much thankful to you on behalf of EC department and GL Bajaj Institute of Technology and Management. Along with management and staff, we welcome you at this forum to know something brief or something detailed, some innovative ideas which will help us in research or something innovation. Normally, we are organizing this FDP faculty development program to gain something from different speakers, which will help us in future to intimate our students like this technology it is enhancing around the world, and this can come only when we sit together and when we discuss about the technology. So, without wasting any time, I request you, sir, please take over this dash and give us some new technology or something brief about the research which is going on in particularly power engineering. So we are very much thankful to you. Once again, I thank you, sir, and welcome to this institute. So at last, one more line I will add. When you are in India, sir, please just remember, because I want to see you in GL Bajaj, and we will be very much thankful to you. Thank you,
Thank you.
sir. Thank you very much.
Thank you. Thank you,
Uh,
Satyendra sir. Thank you, Dr. Asta, for this welcome.
Thank you. Actually, just we will be introducing your profile to the participants, and then we will officially start your session then. So just let me. So, dear participants, it is my pleasure to introduce our speaker for today, that is Dr. Dushyant Sharma. He has received his BTech degree honors and PhD degree in electrical engineering from National Institute of Technology, Rourkela, and Indian Institute of Technology, Delhi in 2012 and 2019, respectively. In January 2020, he joined the Indian Institute of Technology, Jodhpur, as a young faculty associate, where he served till January 2021. Dr. Sharma is currently a research associate at Kansas State University, Manhattan, Kansas, USA. He is associated with the Mike Vegas Department of Electrical and Computer Engineering since March 2021. His research interest includes automatic load frequency control, renewable energy systems, distributed control in power systems, microgrids, and active power control of interconnected power systems. He is a recipient of the POSOCO Power System Award. That's all for about Dr. Dushyant Sharma. Now I would like to invite, and please, sir, you are welcome, and you can now share your talk with us.
Thank you. I'll share my screen. Is my screen visible?
Yes, sir, it is visible.
Okay, so good evening to all the participants, and good evening to HOD and the host. I would like to go through this presentation, which is understanding real-time simulations, and particularly with the emphasis on its application on power engineering. As I understand, this FDP is being organized by Department of Electronics and Communication Engineering. So I believe most of the participants may be from the electronics or communication background. That is why I have tried to reduce the in-depth power system aspects in this presentation, and I have tried to touch more on the power electronics, or mainly the control aspects of power electronics, and give some idea how this real-time simulations can be employed in your research, and it can give you more benefits in your research. I'm sure with this, some understanding of this, you all will get some more insights, and the learnings that we take from this session we should be able to employ those techniques in even in communication engineering or electronics engineering. And I believe talking about electronics engineering, there must be some people with power electronics background who would like feel more comfortable with this talk. So I would just request the participants to be like interactive If there are few things that more which are related to power system or power electronics, which if you face difficulty in understanding, I am happy to repeat so that you can ask questions. And also, when I go through this presentation, if you can answer few questions, if you can interact with me, I think that would be a great way of having this session. So in this session, I will talk about real-time simulations and its application for power engineering. I will start with few small MATLAB simulation demos to build the story and to create the insight that why this all of these things are needed, and why a lot of research and lot of work is currently going on just by using real-time simulators. And I will have couple of videos to show you, to practically demonstrate how these things are actually like working, and how these things actually make our life much easier. So first of all, when I go into the depth of real-time simulation, there are few things that we as an engineer need to understand when we go for simulations, because simulations are very, very important. And right from initiating an idea to its final implementation and testing, everywhere simulation plays a big role. So when we have simulation, what is that is missing in the simulation, and why do we need to go for real-time simulation? How do we do real-time simulation? And then what are the applications, and application not just from the research or publication point of view, but I would also discuss I will just present a couple of real world examples where you will see how these are actually being employed in industries, and people are taking benefit out of these. So first, when I talk about simulations, I hope everyone understand the significance of simulation. If any of the participants can tell me, like, what do you understand by exactly simulation, and what is the role of a simulation in whichever field of engineering you are? How does simulation define your work? If any of the participants can interact, it will be great.
Participants, if you would like to answer, any of you, please feel free to answer. You can unmute yourself, or you can write in the chat box as well.
I will wait for a few seconds. If I don't get any answer, then I'll proceed further. But it's good to have more interaction with the participants, particularly in this online media. We don't see the participant face to face. So it's good to have some interaction.
Okay, we got, yes.
Any answer on the chat?
Yes, sir. There is an answer that checking outputs for real world implementations by my daily.
Absolutely. See, the significance is that when we have a real world process, be it process of any sort of thing, as an engineer, we need to know why and how that system is going to behave, or why it is behaving the way it is behaving. If we directly start a process and just implement without in-depth analysis, and if we go for let's say a product that we manufacture, and at the end of it we find there is a technical challenge, there is a manufacturing error, then it's a loss of time, money, energy, resources. And simulation helps us to solve that problem. We can do multiple test cases right from the inception of the idea to the implementation in the industry. And when we do all of these works, we come up with so many things. We see and observe different phenomena, and then we implement them, we solve them, we find the solution, and we get a better product at the end of it. So how do you define simulation? And simulation is nothing but a study of a model over a period of time. Now, you need to understand what is a model first of all, and then how do we study them. So a model is just a set of equations that represent a physical system. Now, that physical system can be represented in terms of algebraic or differential equations mainly. And solution of these algebraic and differential equations is nothing but the simulation. And the simulation results we try to mimic the actual physical behavior of the device through the solution of algebraic and differential equations. But the question comes, how do we know whether the simulation that we do is correct or incorrect? The results that we are getting are correct or not? For that, we have to make sure that the simulation that we are doing is being done in a proper manner. If the simulation is not done correctly, if we are not doing the simulation correctly, we are just randomly putting few things, then obviously the result that we get will be incorrect. And then our whole objective of doing the simulation will not be valid. So I'll show you just now, I'll show you some small minor simulation examples to illustrate what I mean to say. When particularly when we talk about the simulation in a particularly from a MATLAB point of view, I will be restricting myself because MATLAB is very common to all. We particularly have to think what type of simulation we do. If you read articles, simulation can be divided into many types, but most important, these are discrete or continuous time simulation. Other is fixed step type or variable step type simulation. And then we will also see what is the effect of sampling time. So we need to understand what is discrete time simulation, what is continuous time simulation, what is fixed step time simulation, and what is variable step time simulation. So I will talk about this thing first. This will give you the whole story at the beginning. Coming to discrete time simulation. Now, discrete time simulation is particularly done when you have some systems that actually change their state only at discrete times. What I mean by that is, let's say at t equal to 0, there is some state, and then we add a delta time delta t. Up to that delta t, that state will not change, and the state will change only after delta t. If you can think of any example or any sort of such state, the simplest example which everyone understands is just a square wave sort of thing, or even the pulse width modulation. Right. Now, what we do in PWM techniques, there are states either 0 or 1, and those states only change only after a discrete time, depending on the PWM duty and the switching frequencies and all. So it goes from 0 to 1 and then remains a 1 for a certain time and then comes back to 0, and then remains to 0 at a certain time and goes back to 1 again. Such type of simulations are called discrete time simulations. So basically the systems are discrete systems, and if we have to simulate those systems, we go for discrete time simulation. On the contrary, we have continuous time simulations. Now, continuous time simulations are actually valid for systems which are varying continuously in nature. They do not vary in steps or at discrete times. For example, if I ask you what is the nature of a current that passes through a resistance, if you give a sinusoidal input, for example, 50 hertz that we have in India. So if we give that input, a voltage input to a resistance, the current in the resistance will also be sinusoidal and it will be continuous. It will not change in discrete steps, rather it will continuously change. So such systems are continuous time systems, and their simulation is actually done in a continuous way of the continuous time simulation. But the problem is, when we talk about real world systems are actually a mixture of both discrete time systems and continuous time systems. And therefore, we should do something to have a separate type of simulation for each component, or what we can do, we can use a common method which is applicable for both. And that common method is basically the discrete time simulation. With the discrete time simulation, we can try to solve not only the discrete events or discrete systems, but we can also solve the continuous time events. But the problem is, then our system performance or the results that we get will depend on the time, the discrete time we take for sampling. For example, here, if you see the results that I have presented, so I have put a simple sinusoidal waveform in MATLAB, and I have put a zoomed version here for easy interpretation. So you see, there's a first curve which is pretty smooth like a sinusoidal, which is like a continuous curve. But as I try to do it in steps, the waveform output varies in step. So one step time is this here, and then another step time is this. So what the solver does is it solves as these at these discrete steps, and then if it is a continuous time simulation, it will actually it connect them like a straight line. Or if it is a discrete time simulation, it change it like a step. So it will like keep it constant and then increase it suddenly. So basically, the thing is we can have discrete simulation, but then the another question comes is whether we have to go for a fixed step time simulation or variable step time simulation. This is very important to understand. When we have a fixed step time simulation, our results are sort of more accurate. But the problem with fixed step time simulation is they take more time. For example, if you see again these results here, the step which is there between this point and the next point and the next point is fixed. But if you solve in fixed step, if you have a long or big system that we have to simulate, it will take a lot of time. And therefore, there are variable step solvers. So how this variable step solver works is they see when the system states are not changing fast, they increase the time step. For example, if you see the sine curve around 0 degree or around 180 degree, it's almost like a linear. And if I have a linear curve, just like let's say y equal to t, for example, if I have an equation y equal to t, I sample at t equal to 0 and then I sample at t equal to 1 second, I'll get a correct result. Or I sample at t equal to 0, I sample at t equal to 2 seconds, and then I join them by a straight line, I'll still get as correct results. So basically, my system states are not changing that fast in this duration, and therefore in this duration, if I take a small step or if I take a large step, my system performance will not be much affected. But if you come close to the top region of a sinusoidal curve, 90 or minus 90 degrees around this region, you will see it changes quickly. And in this time frame, if you do not accordingly adjust your simulation step time, you can get errors in your simulation. So although your simulation will be fast, but you have to make sure this changeover of variable step size from large step size to small step size is done in a precise manner. Otherwise, your simulation will not give you correct results. Another thing is, this small or large is just a relative number. It depends on many things. So it just like, first of all, the simplest thing is to understand is the system dynamical range. For example, what system we are studying. If we start with a very fast system, like the radar system, communication system, the communication is like typically very fast, and we have to sample the system in a nanosecond level. If we go for power electronics, where the switching is done in kilohertz or that range, we go for microseconds level of simulation. When we go for power system studies, it typically works around millisecond or sub-millisecond level. And then we know mechanical systems and thermal systems are even slower. So we can go for milliseconds and seconds of level of simulation step when we do such studies. And even in these systems, we have to understand what level of study we are doing. For example, I am giving here two pictures. Now, it may look a little bit complex at this point, but don't see the whole picture at this point. Here, what I want to focus is, we have a PWM inverter. It's a power electronics device which is controlled by a PWM technique, and it is connected to a subsequent power network. Now, this is like a source to this power network, and this source can inject a certain amount of active or reactive power in simple terms. Now, if we have to just study this only the power behavior, then we can reduce this power electronic component of this or the inverter by a simple sinusoidal source, and we can assume that based on the modulation index that we generate through some controllers, we will get output which will follow this reference input, and we can directly assume that there is a reference. This reference that we get from the controller is directly present at this output, we can assume it to be a simple sinusoidal source. And if we have to assume it like a simple sinusoidal source, we can go to that millisecond or sub-millisecond level. But if we have to see the switching components or the switching harmonics and the harmonics that are present in the system due to the switching phenomena, then we have to go to the level of the PWM switching, which is done in the range of kilowatts level, and with semiconductor devices technology is improving. Now switching frequencies is increasing in the 20, 50, people are going towards 100 kilohertz or so. So then we have to go for that much small step size. That is one important thing that you have to understand. Then we talk about the system dynamical range, what type of study that we are going to do. Another important thing is the accuracy versus speed trade-off. As I told you, if I reduce the step size, I'll get more accurate results, but I will have slow speed. On the contrary, it's a very well-known thing that if I change the step size, I will get speed, but I lose accuracy. And then there is one more thing. So these are very, very, very basic things. But then there is one more thing. And this is called the relationship with system fundamental period. What here is your simulation step time should be an integral divisor of the your fundamental period of the system. What I mean is, let's say, for example, in India, the system frequency of electrical system is 50 hertz. And in US, it is 60 hertz. So if you do not make your simulation in integral multiple of these things, these numbers, then you will face some difficulty in certain, not necessarily always, but certain simulations may give wrong results. So I just want to do a small simulation and give you a little bit insight to it, what I'm saying, and you might understand it quite well. So basically, what I'm doing here is I have a triangular or a sawtooth waveform. Now everyone understands sawtooth waveform, and the sawtooth waveform is being generated at a frequency 50 hertz or 60 hertz, and I am going to count how many times this sawtooth waveform crosses a certain number in a certain period. For example, if it is 50 hertz, and I ask how many times it will cross a value of pi in 1 second, it will be 50. So 1 second is a large number. So to reduce it to a small time, I'll make it 0.1 second. So let's say how many times it should cross that number pi in a duration of 0.1 second. So obviously in 1 second, if it crosses 50 times, in 0.1 second, it should cross 5 times. And if I run this simulation and if I show you the results, then it will show something. It should show something like 5, I believe. You see, we are getting 5. This is a very basic, simple thing. We are constantly getting 5. But my simulation type is small. Everything is small. And if I go and change my system frequency, then what is going to happen? I'll just change my frequency to 60 hertz. And then what I do the same thing. I run the simulation and then I observe the same results. And then what will happen? I'll stop this simulation and show you the results. You see, there are some sharp notches that are coming. And sometimes it is counting 6, because in 60 hertz, it should count 0.1 second 6. But suddenly, sometimes it's counting 5. And this is happening because when I change my system fundamental frequency, I didn't change my simulation step time in accordance with the system fundamental period. So if my system fundamental period has changed, if I show you my system step time is 1 by 50 into 160. If I make it 1 by 60 into 160, for example, now, and if I do the same simulation for 60 seconds, for 60 hertz, you will see this thing. Now it is like a constant 6. It doesn't change. It doesn't change. So what is happening here? I'll go back to my slides and so I hope I could give you some understanding of this relationship with system fundamental period. What is happening here when my sawtooth is changing from 0 to 2 pi, 0 to 2 pi like this, and if my system sampling period is not an integral divisor of the system sampling time, then what will happen? My samples are not aligned. And what will happen during a period of initial, I'm doing it in discrete point one sections to give you the idea. People can also do it in continuous moving window of point one, and there are different techniques to solve this problem. But here I am building the story to understand the philosophy that what happens when you don't select a proper sampling time, because it is not always possible to know what is the system fundamental period. And therefore sometimes we may end up in a wrong period, and then we have some techniques to compensate for that, and we can solve the problem. But the thing is, if we go for a fundamental system, if we go for a sub period of a system fundamental period, then our samples are aligned. Otherwise, what would happen? Why did sometimes this spikes came and it shows 5? Because the point which I was seeing when it crosses, the end of one period and the beginning of the second period are exactly aligned, and they get aligned. And for what happens, that for the last count of the previous period and the next count of the next period, first count of the next period, they get aligned. So basically, two numbers are counted as same, 6 and 1, and that is why we lose the count. And therefore, what happens? You do not get the correct results. So therefore, operating the system in depending on what type of dynamical range we take, what accuracy we need, and then what type of system we are studying, what is our system fundamental period. All of these, if we take care, most of the times our simulation will give us correct results. But then the problem comes is this: it takes a lot of time. So we cannot achieve what we wanted to achieve. If we have to do so many testing right from our inception of an idea to actually building of a component and testing it in field, if we wait for all of those components, all of those testing, and we take time, then obviously it will waste a lot of time. So why does it take time? Why does your time is not sync? Some simulations run very fast, some simulations run slow. What is the reason behind it, and how real-time simulators can help us to solve this problem? Why do we need it? What are these advantages? How these are more applicable, particularly from power and control engineering area, we'll see subsequently in this talk. So here onwards, the major component of the talk starts, and previously I just showed you some basic understanding of a simulation. Now, as you might have understood, that we need to have a smaller and smaller step size to get accuracy. But as the system become more and more complex, what happens? It takes a lot of time. And then we cannot integrate this system, this slow, or even on the contrary, if a simulation is very small simulation, it will run very fast. You cannot integrate it with the real system. For example, you have to drive a motor, for example, and you have to control the speed of the motor. Then our normal MATLAB simulation won't work, because the motor that is running is a physical real motor. It will run in the real world's time. It won't wait for the MATLAB to perform its calculation and then give the signal or the something to control the speed. And therefore, this difference of time doesn't allow you to interact with the real world devices. So two major advantages that we get is that we are able to save time. We are able to run the simulation in real time, see what the system behaves in real time, and then we can actually integrate real devices with the system. So it gives you more flexibility, more testing in the lab, as we say, because then you have few components in the lab and few components in the system, and then you can combine them to increase your testing capabilities. Otherwise, everything you need to do only in simulation, because you cannot connect the physical device. So then how these real-time simulators are able to perform real-time simulation and how these works is basically the most important thing. Come back to again the same sampling time. So basically these simulators are nothing but like a computers who have dedicated processors to do this simulation that you do in a normal MATLAB simulation, but these perform their action in a predefined time. And this in a predefined time, they take the input from the sensor or the physical world, they do the calculation and give the output. in that predefined time only. So how these real-time simulations evolved over a period of time. Typically, simulations we are all doing right from like many years. But previously, if we had to do simulations, then the simulations were being done in analog form. For example, if I had to model a transmission line, what would I do in a lab? I will put a component. I'll put small sized resistance, inductors, capacitors, and I'll connect them to form a transmission line, and I'll see the performance or the behavior of the transmission line. So that is nothing but a complete analog world. But in the 90s, these digital simulators started, and the sort of this first which started is this hybrid of analog and digital simulators, which were mainly based on DSP and some analog components and op-amps. And then came the era of these CPUs and like the CPUs that you have in your computers, normal computers. Those multi-purpose computing systems started to come up, and people started to use them for real-time simulators. And then what happened? Starting from analog to hybrid of analog and digital, and then we went to complete digital sort of these simulators, and then the digital simulators give us benefit of speed, flexibility, and all of them. So Arene was one of those first fully digital platform, and then Siemens made this Netomac, and there are many more. But currently there are few like OpalRT, DSpace, HyperSim, RTDS. These are particularly this OpalRT, DSpace, and HyperSim. They are completely digital, CPU based or FPGA based. So even now in the digital world, the research has progressed to two things, which is the CPU core or the FPGA, because FPGA give you more flexibility. So now with this digital simulation, we can perform all of these things in real time. So how this works? They take input from a normal computer, typically just like a MATLAB simulation that we do, and then they convert it. They have some software or processing units which convert them to C codes or SDL codes, and these C codes or SDL codes are dumped on the real-time simulation platform, where these calculations are now done on these different computers, and they sort of do it in real time. And there are many manufacturers, so I'm just giving you few examples here, just like OpalRT, DSpace, Typhoon HIL, RTDS. These are few major big players in this industry. So basically, how we do that is very simple. I'm not going into any of the particular software, just giving one example here. RTLab, they all have some sort of either some software, or you can integrate your MATLAB files with them, and then basically, as I told you, convert C codes from them or SDL codes, and then export those SDL codes to the actual simulator, and then the simulator executes the code, and you can see the results in either their platform or the MATLAB or whatever its type of integration is. But this is important to understand how these simulators are actually helping us to do real-time simulations. So the first two figures that you see, this one and this one, these two are offline simulation, just like we do in MATLAB. And what happens in these simulations is that you have some input, you have some calculations, you have some output, and you have a step size. Now, if your system is very, very small or very simple system, then this calculation of this, taking the input, processing the input, and giving the result, all of this will be done in a time which is lesser than the step size. Now, there is some time left, and you have already done the calculation. So what this processor will do, this processor will start doing the next calculation. It will start doing the next input even before the next step size. That means even before the next step time of the real world, I'm saying. So this is the, let's say, real world clock. So if you have given a delta t step size in simulation and correspondingly delta t in a real world clock, so what will happen? It will start to take these inputs and it will start to do these calculations. So compared to real world clock, the clock of the simulation is sort of running fast. It is doing its performing its simulation faster, and therefore this simulation will run faster than the real-time simulations. But on the contrary, if you reduce the simulation step size large, or if your system is a big system and it takes a lot of time to do the calculation, then taking the input, doing the calculation, and giving the output will cross this step size limit. So basically, compared to the real world, to do one calculation in the delta t time will be more than the delta t time of the real world. And therefore, now it's sort of a lagging thing. So the first one was leading thing. This is sort of a lagging thing. This will be slow simulation, and you will have to wait for a lot of time to get the results of this simulation. So this is what typically happens in offline simulation that we typically do in MATLAB. But how do you solve this problem in real-time simulation? So in real-time simulation, both these scenarios are solved by either delaying the calculation or stopping the calculation. What I mean is, let's say you, in the first case, you do the calculation before the real world clock ticks. You have still time left. In a normal MATLAB simulation, the next calculation would have started. But here, it delays this time, and the next calculation starts only after the next step size. So therefore, what happens? You always perform each calculation, each delta t time, which is synchronized with the real world time delta t. On the contrary, if you have a small step size and the calculation cannot be done in this step size, what will happen? The next step size, there will not be any calculation, and in the subsequent step time, your actual calculation will start. So this scenario we do not want to occur, because then this will give you wrong results, because you are not simulating the entire system. You are missing the simulations during each alternate simulation step. And this scenario we typically call in the field of real-time simulation as the overruns, and you typically do not want such a scenario to happen. And therefore, your system should either be running well within this, or you have to do something to either reduce the system complexity, or you have to increase the step size, so that within one step size you do the calculation completely. But again, if you increase a lot, then again you will lose the accuracy. So therefore, accuracy and a real-time trade-off, and then what techniques are actually used to solve these problems. So there are different phenomena. One is called multi-rate simulation. In the multi-rate simulation, you have different sections of the whole system which works on different rate. For example, let's say if you have a power system connected with a power electronic device, so the power electronic device will run at a faster rate, while the power system will be simulated at a slower rate, and there can be ways to integrate these two different time steps. That is called multi-rate simulation. Another thing is multi-core processing. So just like you have in your computers Intel multi-core processors, just like in these also you have multi-core processor, and you partition the model. So the simulation model that you have, you divide it into certain cores, and each core run the simulation in a parallel way, so that the resultant time that is required to do the simulation is reduced, and then you can go for a smaller step size, and still you can operate in real time. And then nowadays, even people are going for FPGA based processing, because FPGA gives you the flexibility to do the paralleling as you desire. It's more flexible, and therefore, if you have to go for a switching frequency of like 100 kilohertz or so basically if the time period is like in the tune of nanoseconds, then we go for FPGA. So therefore, nowadays these real-time simulators are coming with CPU based as well as FPGA based processor. So when you select a real-time simulator, you have to see what is this computing power. One thing is the simulation step size, but also the number of nodes it can simulate. For example, if you start with a simple, let's say a simple generator connected to a load, it's just a very small system. But if you see a complete Indian big power system, it's a very big power system. It's of so many nodes to solve. Then, even though you solve at a little bit higher step size, your computation power requirement will be still too high because you have many nodes. So basically, there is a trade-off between the number of nodes and the desired step size. If our number of nodes increases, our then step size has to be accordingly large. You cannot go for very high frequency sampling for this case. So your computation power is a resultant of both these techniques, both these two things. One is the number of nodes, and one is the desired time step. I won't go into much of these details. These are more computer engineering thing, but just to give you some idea, there are basically two type of simulators. These are basically depend on the processor that we have. But in the modern days, which are, as per my understanding, which are more running is this second type, which are CPU based, which have multiple core CPUs. Plus, they have also FPGAs to handle the high frequency component. As I told, even the PB5 processors also. So basically, these are rack mounted processors, and more for like computer engineering point of view. They have more communication protocols and all. They also have the flexibility of now coming with FPGAs. So basically, you have to either simulate in the core or the FPGA. But now, so that was more of the computer architecture of the real-time simulators. But how do we use for our purpose as a control or as a power electronic engineer? There, for our system, we have to see what type of study we need to do. One is electromagnetic transient study, one is phasor-based study, or there could be hybrid of these two. So electromagnetic transient study is basically faster dynamics that we try to capture, which are the electromagnetic transients. The phasor study is basically the electromechanical transient that we typically do. So then, in the case of phasor transient, we solve the system at the fundamental frequency, which is the 50 hertz or the 60 hertz, in the form of phasors, and our step time is could be large, like 20-30 milliseconds. But for the electromagnetic transient, we need to go for a little bit high frequency sampling, and we could see the switching components like non-linear devices, power electronics, and all of those things. And as an engineer, as a researcher, when we try to employ these aspects of real-time simulations, we do typically three type of applications. One is control prototyping, other is hardware in the loop, other is fully digital simulation. People also call it software in the loop, controller in the loop type of words they use, but typically they have the same meaning basically. So first one is the controller prototyping. As I told you, the most important advantage that we people extract from these simulators is the capability to interact with the physical devices because they run in real time. So then what options do you have? One option is to simply run the whole simulation in just simulation, no physical device. Everything is simulation. The advantage, as I told, is like to have the simulation in a faster time on real time. So you get a simulation which is completely fully digital simulation. You have a plant which is in simulator. If you want to interact them with the real world, how do you interact? So let's say we have a real physical system. For example, a real power electronic converter, a DC to DC converter, or a DC to AC converter. And so basically you have a real physical system, which is a plant. And you have a real-time simulator in which your controller is working. Just the controller is in the real-time simulator. Through the help of inputs and outputs, you can connect that device with the controller. So there will be some inputs, some outputs. So in the form of analog and digital, the real system will give you analog values. That these analog values you give to the controller, it will process in the digital form and give you some signals either in analog or digital form to run the plant. That is called control prototyping. This gives you the advantage of testing your controller with the actual system. And there could be a reverse phenomena, which is called hardware in the loop, where we have the system, the physical system is in the real-time simulator. For example, let's say you want to model a big Indian grid. If you want to model a big Indian grid, you cannot have in your lab, basically. So then the big system will be in the simulator which is your physical system or plant in the simulator. But let's say you want to have a controller, microcontroller, physical microcontroller, you want to test its performance. Then what you can do? You can connect that microcontroller with the real simulator, and because the things are working in real time, there can be the flexibility of again connecting the analog or digital input output channels, and you can test your controller performance. So the thing is, now when you do this, the thing is either one of them is in completely in simulation, only one of them is in hardware, but the power exchange, because the controller, these real-time simulators, these computers or the microcontrollers, they are low power devices. They take low voltages and low currents. So basically you need to change the actual values to appropriate level to make them work, but that is not always possible. Sometimes what happens, your hardware under test may have high values of voltage or current. Sorry. So therefore, you need to amplify or do some sort of signal conditioning, and we put an amplifier in between to connect with the real-time simulator. And the amplifier basically changes the voltage magnitude or the currents to interact with this hardware, and the amplifier is now controlled by the real-time simulator. But a typical amplifier either amplifies the voltage or it amplifies the current. It cannot amplify both. So therefore, particularly for power electronics or power system point of view, we now coin a new term, which is the power hardware in loop, which is a very important, particularly for our research area. In power hardware in loop, we use a power amplifier, and the power amplifier can now amplify both current and voltage. That means it can amplify the power. And when you go for a power amplifier in your HIL test, it's called power hardware in loop, where you have a real-time simulator, you have an amplifier, and you have the hardware under test, and which are all connected through the input-output channels. And when you employ power amplifier in your system, then power amplifiers can be divided into 4 categories, basically 4 quadrants: first, second, third, fourth. You can see from this graph whether the current is positive or the voltage is positive. That means either the power amplifier can produce both positive voltage or negative voltage. Either the power amplifier can deliver current or absorb current. Basically, the power amplifier can behave like a load or a source. So if you see the first quadrant, voltage is positive, current is positive, P is positive. That means it can deliver power. In the third quadrant, voltage is negative, current is negative, so it is still delivering power because the resultant becomes positive. While in the second and fourth quadrant, the multiplication becomes negative. That means it's absorbing power. So there are different types of amplifiers. I'm not going into details here, but the amplifiers basically can be divided into 2 main categories. One is the linear, and the other is the non-linear. And our output, how does our output change? What are the bandwidths and what flexibility you get? So with a non-linear one, you can also model the switching things, and you get more sort of flexibility. So what flexibility you use based on your requirement, you can select a power amplifier and connect in between. So one example which I want to start with in the case of a power hardware in loop. For example, let's say you have an inverter. Let's say, for example, a solar photovoltaic inverter. Now, a solar photovoltaic inverter is connected through a DC to AC converter to a 3-phase grid. Now, you have a DC source like your PV. You want to see how the system performs. What we can do here is, in this case, we can have an actual controller sitting outside in the real world, and it can interact with this converter, and it can inject power from the PV to the grid, and you can see the performance of the system. This is what your control prototyping is, what we discussed just now. But with the help of a power amplifier, let's say you just have a physical inverter and a physical controller, but you do not have a physical PV for photovoltaic or physical DC source, or you do not have a physical 3-phase grid. Then how do you connect them? So in between this is this power amplifier. So what the power amplifier can do, it can be regulated through the real-time simulator based on the DC source characteristic that you want to mimic, just like for example, a photovoltaic. So now this real-time simulator will control the power amplifier, and it will give you output just like a solar photovoltaic. Your converter will be controlled by a actual physical controller, just like this, But here the controller was controlling the inverter in the software. Here the controller is controlling the device, physical device. Now, because this is a physical device, it will generate some real power, and that real power has to be dumped somewhere because energy has to be utilized. So again, there will be a power amplifier that will use that energy, and then it will connect it to your power supply that you get in your labs or wherever you are working. And this power amplifier will again be controlled by this real-time simulator, depending on this input-output channels. So this is how your power hardware in loop helps you to physically check few components of your system which you physically have, and you can interact them with the simulation platform through the help of real-time simulators. So I hope you people are following me. I'll just give one more phenomena of the real-time simulator need for compensation, and then I'll go for its application demonstration. So the important thing is, when you do these real-time simulations, there is one phenomena which is called the jitter phenomena, and we need to compensate for jitter phenomena. The jitter phenomena is like this. Let's say you have, because we have understood that we do the simulation in discrete times, but if our event occurs sometime other than the time of sampling, for example, this is a circuit where this AC source is connected to a inductor through a thyristor. Now, if you turn on this thyristor, your sampling is here, and the thyristor is turned here, so few microseconds earlier, but the sampling will be done here. So the system will assume that the thyristor is fired at this point, and their waveform will be different. And therefore, so the difference will between the actual firing and the sampling instant will lead to different sort of results. And therefore, now the modern day real-time simulators are coming with these compensation techniques, which if you remember this figure that I showed you, here the input is done, calculation, this output is done, and then the input is given to the next step time. Not just the input, but some more information is given that what has something happened to the system during this sampling instant. And if something has happened to the system, it compensates for it in getting the result, and it gives you more sort of accurate results. And therefore, this compensation of jitter phenomena also helps you in getting more accurate results with the help of real-time simulators. So if we have understood the basic functionality of a real-time simulator, I would like to go into the applications point of view. I think we have done almost 1 hour, and I would just like to ask if you have any questions, and if you people are following up to this point, any questions, or if you want to discuss anything.
Participants, feel free to type in the chat box if you have any questions to ask, or let us know that you are following.
Yeah. Is there anything in the chat till now, Dr. Asta?
No, not after that.
Okay. Participants, are you following?
Dear participants, please, we would be feeling grateful if you could motivate us by just simply writing that you are following. I think so.
I think. Okay, so let me proceed with this. And now we'll talk about more of the application point of view. And as I told, more applications, my research is more oriented on the power system point of view. I won't go into the much technical depth of it, will give you some understanding. So basically, these real-time simulators are not just used in power engineering sort of, they are like nowadays used in almost every field that we actually have, right from inception of the idea. So this type of curve is called the V curve, where it's like from validation to verification. You design something, you prototype it, you implement it, you test it. All of these things can be done with the help of these real-time simulators. So It is used in particular from the power point of view, power system protection, renewable energy integration, power electronics, electric vehicles, train and ship applications. I will just give examples here, one by few of these: industrial drives, aerospace, robotics, and I'm sure there must be some communication application as well. So basically, when you have some idea, what you do, you simulate it, and then you try to integrate it with some real-time devices to further test it. When you think this works well, you prototype it, and then with the prototype can be integrated with another system in real-time simulations. Then when your prototype works well, you can implement more test cases. You can test with different scenarios again and again, and then you can see how the whole system is behaving. And therefore, right from validation to verification, you get the overall understanding of the working of your device. So I will just give few examples based on my research, and few example which I could just see in literature to understand, to make people understand how these things work. So, for example, in one of my papers, I developed a power system stabilizer, and now, well, power system stabilizer is a well known thing in power system, but coming to the modern aspects and more communication intensive power system, there can be delays in the governor control of a system, of a power system. So the governor control is that part of power system which regulates the system frequency. For example, the one we get at our homes is 50 hertz. So basically, how do we regulate that 50 hertz? We regulate them by controlling the steam that we inject to the thermal power plants or so. That is done with the help of governors. And if there is a delay in the action of that governor, our system stability can be hampered. Our system can lose its stability. So with a small system, I have shown here in a simple transfer function domain, I have shown here that my system can get unstable due to negative damping. So I'm not going into the details here, but this negative damping is introduced due to some component which is related to this phasor diagram, just for understanding. But basically, what I want to show here is that these oscillation, this system instability that occurs in this system, in this frequency control loop, is a very low frequency component. If you see the time frame, one oscillation takes almost 50 seconds. This is a very low frequency. To study these very low frequency components, you have to run the simulation for a very long time. And then our objective is, as a research, is not just to find problem, but to solve these problems. So what I have done, I have developed some sort of stabilizer which actually solves this problem and stabilizes the system. So if we see in these results, the original system is marginally stable, and then with my stabilizer, the systems become stabilized. But the problem is, this was a very small representation of actual system, and system this system may not be the true representation what happens in a power system. So what we can do, we actually have to test this phenomena in a real system. Now you see, when I took this small model of a system represented by their simple transfer functions, I could easily solve this system in MATLAB up to 300 seconds, and I could get the results. But as soon as I start to do it in a big power system, then running it for 300 seconds or so will take a lot of time. It's like 300 seconds, it's like one day it will take. Then this power system, this real-time simulators comes to the rescue. So what I do, I actually model a standard power system, which is called a 3-machine 9-bus power system. It's got 3 machine synchronous generators and few networks, and this is a very big rated system. This system, now it's a big system, it will take a lot of time in real simulation. I will simulate it in the real-time simulator. So if I can simulate it in real time, I can see the real-time behavior. It will give me quick results. Everything is simulation. No, it's not HIL or control prototype. both the controller and the system plant, that means the whole system is in real time simulator. But because it is in real time, I can connect a physical device and I can see the behavior. So I can actually see the results on a DSO like this, because the system is running in real time. So I need not to see the results in MATLAB window, and I can plot the real time results in a DSO like this, and I could very quickly see the results that I wanted to get. So what I do, I make the same system in MATLAB, and I dump the C codes in the simulator as I told you, and then I could run it in real time and I could see. So I could get very low frequency components. If you see the time frame of the DSO results, it's like showing results for 100 seconds. So it's actually showing results for 100 seconds in actually real 100 seconds. And I could demonstrate in a real system that if the system is marginally stable under certain scenario, when we employ the stabilizer that I have developed, it actually reduces these oscillations and make the system stabilized. So basically, something that you develop, and if it needs a lot of time, you can actually just simulate in real time and see the behavior. This is one example of the pure digital simulation case. Then similarly, next, where you can use from a power system point of view is a power system protection. In power system protection, we have relays which give command to circuit breaker. For example, when there is a fault in the system, so the relay will detect the fault and it will tell the circuit breaker to disconnect the faulty circuit or something. So now again, if you have a big power system to study, just like this, just like in the previous case, you can operate the system in a real-time simulator, and you can connect the physical relay which you want to study accordingly scaled, because these components, these microcontrollers, all are low power rated devices. So you have to scale down the measured voltage and current, and accordingly the calculation can be made, and you can give the same signal back to the main simulator to detect the circuit in the simulation only. So this is how you can actually connect the controller sort of in loop sort of thing, where you have one physical device controlling any component in the circuit. So coming to controller in device sort of thing, and as I told, I'll mainly talk about power electronic converters. So the power electronic converter testing can be easily done, and real-time simulators are a lot of being used in power electronic converter testing. So you have a DC source, you have a power electronic converter, let's for example a PWM inverter, and a PWM inverter is connected to a filter to filter out the high frequency thing, and then it is connected to a three-phase or single-phase grid, whatever case may be. So now if we have to control this system, how do we control it? First of all, we have to understand its control philosophy, and we typically control a three-phase converter in DQ domain. So you might have heard of this. This is called Parks transformation, and Parks transformation is converting ABC quantities to DQ0 quantities. Why do we do that in the first place? So basically, ABC quantities, that the waveform that we get our homes, are all sinusoidal quantities. And when you have a sinusoidal quantity, something which is time varying is difficult to control, and therefore it is easy to control something which is constant, which is like a DC. A PI controller, typical, most simple industrially acceptable controller is a PI controller, which works the best with a DC things, constant things basically. Now, how do we convert these AC quantities to DC quantities? By the help of a Parks transformation given by this matrix. And this Parks transformation, actually what it does, it gives you two components. One is VD and one is VQ. And people use different convention. And the convention is to use one of them as 0, one of them as the rated. So how do we make one of them 0 with the help of a PI controller? We obtain an omega, we start with an omega, convert it to theta by integrating it to theta. We give this theta as an angle to this Parks transformation matrix. We get VD, VQ. And one of these two, VD or VQ, we have to make 0. So we give this to path transformation, which is ABC to DQ. We get the VQ. So your VD should be the rated V and your VQ has to be 0. So we compare it with a 0 and the PI controller adjusts the frequency in such a way, then the resultant frequency which comes out gives you the theta, and then with this theta we can actually get a constant VD and VQ as 0. Why do we need this? We need this because the three-phase supply or the supply that we get our labs or at our homes is constant. We cannot play with it because it comes from a large power system. We do not have the capability to change it. Therefore, our voltage that this inverter produces has to be synchronized with this voltage. It has to be in the same phase. It should carry the same phase angle. For example, if I write the any sinusoidal waveform Vm sin omega t plus theta, so that theta should match with the theta that this inverter produces. Otherwise, there will be circulating currents because you cannot change the theta voltage magnitude angle of the grid. Vm sin omega t plus theta, Vm, theta, omega, all are defined by the big grid, and we have to connect to this grid. So basically, what we do, we develop a control technology to control the PWM inverter in D and Q axis. So what we do, we write the equations. So basically, this filter that you have here is, just take a simple example, a simple consideration of R and L. We write the differential equation of this R and L circuit, and we convert the differential equation to D and Q form. And when we convert the differential equation to D and Q form, we can control the system separately along the D axis and along the Q axis, and then accordingly we can generate the PWM signal. So what we can do, we can basically take the DC source, and basically this is your actual inverter connected to the grid. We have an DC source, a voltage source converter, you have a filter, you have an AC grid. You have, first of all, you need a measurement. And now with the help of a measurement, you give the current signals and the voltage signals to the controller. So all of this is the controller. What it does, it actually gives your voltage to the PLL, gets this theta, and the same theta is used for ABC to DQ transformation of currents and voltages, and then you calculate the active and reactive power based from these ID, IQ, VD, VQ. This is the D and Q axis components. These P and Q are compared with the reference P and Q that the inverter is required to produce. For example, let's say the inverter is required to produce 2000 watts at 0 reactive power. So some reference is given to the controller. You measure the actual P and Q, get the error, pass it through PI controller, give this PI controller will give you the current this inverter should inject to meet that power, because as I told, this voltage is now fixed by this grid. So because the voltage is fixed, to change power you have to change the current. So basically this controller will give you the current that you need to inject into the system. And to inject the current, what you will do, then you will measure the reference. You will have the reference current which is coming from this PI controller, and you have the actual current measured, ID and IQ. These actual currents are also subtracted from the reference current. There is an error, there are PI controllers, and this PI controller actually produces the voltage VD inverter and VQ inverter. Now these are the voltages that your inverter will produce at its terminal. And how will it produce at its terminal? Depending on the modulation index and the PWM frequency. So the modulation index is related to the output and input voltage. So you have an input voltage which is a DC voltage, and you have output voltage, and these are related by the modulation index. So your output voltage, you multiply it by 2 by VDC. VDC is your input voltage, and you get the modulation index. Based on this modulation index, you get the PWM generation for this voltage source converter, which injects the certain amount of P and Q. So basically now this controller we can do in two ways. One is we can have control prototyping, as I told, where you have the controller in a real-time simulator. So controller is in the real-time simulator in this box that I've shown you, and the other is the physical device where you have physical DC source, physical inverter, physical RL lines, and physical grid like this. And you have to control this whole of this physical system through a controller. So you can make your controller in a real-time simulator, and you can test it multiple times with different type of gains and different type of controllers, and you can see how the system behaves. And the reverse can also be done. The reverse is the hardware in loop, which I just mentioned earlier. It's like you have a physical controller. So controller is physical, and the system is in real time. Let's say you don't have a real inverter. So the system is in real time, and you want to connect this power electronic converter. So these two cases, I just want to just show a couple of videos for better understanding. Just give me a minute. Dr. Asta, is the video visible?
Yes, sir.
Okay. So now, as I told you, one method is you can have if you want to test your controller and you don't have a system, then you can make a system in your simulation. So for example, we have a complete system. We're starting with a DC source to a voltage source converter to a filter, and then the grid, and these are your grids. So what you do, you measure the currents, voltages, and you give as analog output of a real-time simulator. So this is made in a real-time simulator. It is in the software which is called Typhoon HIL. I'll just show you. So this is the Typhoon HIL, which is a real-time simulator, and it has analog and digital input-output ports. So this analog signals from the measurement goes to a controller, and now my controller is a physical controller. So this one that you just saw here is a DSP based physical controller. This controller does the same calculation which I just showed you and give the PWM signals back to the real-time processor, and the real-time processor accordingly generates the signal. So for example, I just showed you a number 2000. Basically, it is producing a active power of 2000. And if I have to see how my controller performs in the case of when I change the reference to, let's say, a large number, for example, 10,000. So I will change this number to 10,000 in my controller, and my controller will accordingly generate the pulse width modulation signal that will go as a digital input to the real-time simulator. And you will see here, my active power has started to increase, and my active power goes to 10,000, which is my reference. And now I can analyze this behavior easily. There is some background noise. Can the participant mutes, please? Okay. So see, we can now analyze our system, that how my system or how a controller is behaving, how much time it takes to reach to the desired value, how much is the overshoot, how much is the undershoot, what is the settling time, and I can retune the controller parameters. And there is no chance of physical damage because there is no physical converter, physical system there. Once I have tested my simulation, everything, I can implement the same thing in a physical system, where I can now have a physical inverter connected to a grid just like this, and I can actually do the same testing with more confidence. So I'll just show you one more video like this. So basically, now we have a complete physical hardware, and it is injecting some power. So if you see the power values here, it's showing 98 watts. We will change the reference. So once we change the reference, you will see on the screen the number changes in a real system, and it starts to inject more power. So we made the reference at 200 watts, it starts to inject 200 watts. That is how a real system then works. So how it is working, now we have a real system. We have a real DC source which is controlled by a controller. Now the controller is in real-time simulator. So I changed the reference from 100 to 200. It went to 100 to 200. And in the real-time simulator, I can compare the performance of my whole controller. I can see different signals, how my controller is behaving, what is the overshoot, what is the undershoot, everything I can see for a real system now. So I will just go a little bit quick. my real system. We have a DC source. This is the DC source. This DC source is giving power to a physical inverter, and the inverter is being controlled through another real-time simulator, which is called the D-space real-time simulator, which is connected to this computer. So this is working like this. This is my physical inverter. This physical inverters, there are sensors to give signal to the real-time simulator. So through these wires, I give the measured signals to the through these wires, I give measured signal to the real-time simulator. Through these wires, I give the pulse width modulation signal to my real inverter, and that is how my real inverter works. And you can see that the controller which I tested in offline simulation, basically in control prototyping, that type of controller actually works well in the case of the second scenario, which is the hardware in loop, where you have a system, and then you have basically controller, and all of them are being controlled. So more type of PWM techniques can be employed, and you can test different type of control schemes. Another type of inverter, which is particularly nowadays very important from the power electronics point of view and power system point of view, is the grid forming inverter. For example, at your homes, you have inverters. When there is power outage, your inverter produces the required voltage. So there is no grid. It need not to be synchronized with any grid voltage, phase angle, or magnitude. It can produce its own voltage. So basically what can happen, now the controller will change. Now the objective of this controller is not to produce the P and Q, rather not to control the P and Q, rather it is to control the voltage magnitude. So again, we control the voltage magnitude, and again along D and Q axis, and we have a similar inner loop, which is the current loop, to regulate the current. But now the current reference comes from a voltage control loop, contradictory to the previous one, where it comes from a power control loop, where we calculate P and Q and we control them. Here you have V voltage, and the voltage is again divided into two axes. As one axis, as I told you, we try to make 0. So we typically try to make this VQ star as 0, VQ reference as 0, and VD reference as the required voltage. For example, at our home, we want a single phase 220 volts, like that. So basically this reference we give, we have PI controllers which give the current reference, and this current reference is compared with the actual current, and then we again get the modulation index, and then that modulation index generates the PWM, and the pulse width modulation is given to this power electronic device, which regulates the system. So I'm showing for this is AC grid. Research is also going on DC grid, where you have DC to DC converters like buck converter, boost converter, like these. Similarly, you can control all of these in the similar manner. And then once you design your controller, again the same thing can be done. Either you can do the control prototyping, or you can do the hardware in loop, where you have a controller in real-time simulator and you have physical devices just like I showed you, or you can have hardware in the loop, where your system is in real-time simulator and your controller is a physical controller. So like this, you can also do it for grid forming applications of an inverter, or autonomous inverter we call it, where the inverter produces the required voltage and frequencies. Then you can extend it to many applications. So I will just quickly go through few applications that I have done in my research, and I have gone through the literature. For example, now let's say you have to control a big microgrid. So even to control big microgrid, these converters, these simulators have the capability to, as I told, to have simulate big nodes. So basically, this is a microgrid which I have developed at IIT Delhi, and what I'm trying to do is that I'm trying to control many sources at the same time, and I have developed a control philosophy which is based on the disturbance observer technique. I'm not going into the techniques, but these are listed in my publications. But what I'm saying is, how I am building this whole setup is like, in a simple term, it can be represented by this simple single line diagram, where you have one synchronous machine you have transmission lines, you have loads, you have transformers, and then you have these PWM inverters and with their filters, as I just told. But this synchronous machine is actually being driven by a DC motor, and the DC motor is driving this synchronous generator. Now, how many things I have to control? So when you have a DC motor, the DC motor will have this DC motor field, it will have DC motor armature, and you have the synchronous generator. The synchronous generator will have its own field, and accordingly it will produce the DC voltage. So you have these buck converters, you have these voltage source converters, and all of these converters, power electronic converters, are being controlled using the controller in real time, which is in the OPLRT real-time simulator that you can see here. So basically this system is everything here that I've shown here. Now, what is the role of real-time simulator here in this system is like this. As I told, there are 3 buck converters. One is to control the motor field, one is to control the motor armature, one is to control the generator field. So all these 3 buck converters are actually controlled using the controllers that has been developed. First thing is a motor armature voltage. For example, a motor is, let's say, rated at 200 volts, for example. So then you have to produce 200 DC voltage from the DC source, and the DC source may not be necessarily the same voltage. It may be a little bit high or a little bit low. In my case, it's high, so I'm using a buck converter. If it is low, you can use a boost converter. So now, to control the voltage that is injected on the DC motor armature, you need to sense the armature voltage and armature current. So we have physical sensors. These physical sensor reduces the level of the actual signal, and then it gives to the simulator. So in the simulator, to actually have an idea of the actual signal, you have to multiply with the scaling factor of the sensor, and then it gives you the necessary control action. When the necessary control action, it will find out what should be the duty ratio of the switching of a buck converter, and then it will generate the switching pulses accordingly. So one is to control the field armature voltage, other is to control the field voltage, and then you can subsequently add further layer of controls, because one is to just control the field voltage, other is to control the motor speed. Let's say I'm using a field weakening control for motor. So in that case, I also need to give the speed as the inputs. Then I need a tacho sensor. So the tacho sensor will also be there connected, field voltage, field current, all of these through the sensor in the reduced levels will be given to the real-time simulator. There will be a controller developed in MATLAB. It will generate the PWM, the duty cycle of the buck converter. Then when the motor runs at rated speed, the generator will produce a voltage only when there is a field supply. So to produce the rated terminal voltage at the terminals of the generator, what you need to do, you need to change the generator field voltage. And therefore, to control the generator field voltage, we need to again give generator field voltage, generator field current to the controller. Also, as I told, the controller is being controlled to control the generated terminal voltage. Therefore, the terminal voltage is also given as an input. And then again, the controller is developed in MATLAB, which runs on the real-time simulator. It gives the switching for the buck converter. So these are the 3 buck converter switching which is done. And then there are voltage source converter also. So in one voltage source converter is fed by a solar photovoltaic. So when it is fed by a solar photovoltaic, we know in the case of solar photovoltaic, we want to operate it to maximum power. We call it MPPT tracking, that it should always extract the maximum power from the solar photovoltaic. To extract the maximum power, you need more sensors and more measurements. So you give the PCC, which is the point of common coupling. That means where this filter is, where this inverter with this filter connected. So at this point is called the PCC, point of common coupling, where we give the PCC voltage, PCC current, and the PV voltage, PV current, all through the sensors and scaled values we give again to real-time simulator. And then it produces the switching, PWM switching for the voltage source converter. And then there is one more voltage source converter here, which I am using to generate a desired active and reactive power. So based on the requirement of the active and reactive power, so that, as I told just earlier, the active and reactive power is controlled by sensing the voltage and current, and then the controller will be taking the necessary action to give the PWM, and therefore you will get the voltage source switching PWM for this voltage source converter. So you see, all so many things, and even more we can just add depending on the capabilities, depending on the core, depending on whether we are using CPU based processor or we are using FPGA based processor, and we can test our algorithms with such thing. And the advantage that we get is we can test, because now you can change you can change in real time. You can see the performance of your system under different conditions. For example, I can see what happens when there is load changes occurring. I can see what happens when there is a PV power changes occurring. So when there is a PV power changes occurring, I can see how my system adjusts, how what is my system frequency. If there is a sudden load change, how my system frequency is restored, because you always want to operate at a system fixed frequency of 50 hertz, for example. And if your controller parameters change, or if you use a different type of, for example, if you develop a new type of controller and if you want to compare with any of the classical controls, so because it's just a simulation that you need to change or some parameter you need to change, you can do it very easily, and you can compare the performance. So that for the same scenario, I can compare the performance of two type of controllers in my system. So that is how I can work. So that is mostly related to power electronics, which I have just touched upon. I'll just go in few 3-4 slides, just give you broader perspective that it is used to test so many devices. For example, in this paper, they have used RTDS simulation for fault current limiter testing. So there is a big power system. There is a this superconducting fault current limiter. So basically, in a power system, when there is a fault, there is huge current. So, for example, there is a fault here. That means the phase is connected to the ground. So there will be very small impedance. There will be large current. So if you have to limit that current, there is fault current limiter. To test this fault current limiter, the whole system is developed in a RTDS simulation, and then there can be physical relays outside the simulator, and you can again, through the analog and digital signals, you can connect. So basically you can test the power system control, you can test power electronics control, you can test power system protection. And just to give you a glimpse of how people have used to simulate big systems, if you see, this is a real system which is called the Hydro-Quebec power system, which has been simulated in real time in this paper, where they have shown such a big system. What happens to this system when fault occurs and when there is large penetration of wind energy? So nowadays, wind and solar are the prime things which are increasing, and also electric vehicles. So in the large presence of these things, how your system is gonna perform? You have to test a big system, let's say India level system, and then you cannot just simulate in normal MATLAB, and then you need to have a fast real-time simulation. So basically, this is the Hydro-Quebec network, and in the Hydro-Quebec network, there is a small area which is called the Eastern network, and the Eastern network itself look like this. And you see there are multiple wind generators that people have touched, like integrated and tested what happens in the case of fault. As I told, communication can also be tested the performance. So if there are multiple relays, for example, connected to a big power system being run in simulation, and we can also see how the system performs when there is communication being involved. So if these relays are being used remotely or controlled remotely through a remote computer, which is with a controller or something, so in the presence of communication delay or communication channel failure, how the system will affect and what will be the effect on the big system, again you can incorporate all of those things. And modern these real-time simulators are coming with communication protocols and everything, so that as a communication engineer, all of these can be implemented and can be tested. Another important aspect from a power engineering point of view is the HVDC, and this is a real implementation of HVDC on an ABB system. So ABB has got these MAC controllers to control HVDC, high voltage DC systems. Now again, to see the performance of the their MAC controller, ABB tested all of these on a HVDC system. So the HVDC system was actually implemented in a real-time simulator, and then the controller was just used to integrate and see the performance of the controller. So basically, before implementing the control in a real field, you can do n number of tests in a real system with different scenarios, and you can see what are the failure chances or what are the issues, and you can work on. As I told, EV charging. So nowadays, electric vehicles are coming big time, and if there are big electric vehicle charging stations, what will happen? They will consume a lot of power, and then utility has to take care of all of these charging infrastructure, because electric vehicle give a peculiar scenario that they are charged and discharged based on time. For example, if you charge at home, people will typically come home after office in the evening or night and then will charge. Or if they are charged at parking lots of the office buildings, then people will reach around 9:30 that time, and all the people will start charging their vehicles. So there will be sudden load on the system, how the system will behave, and again, all of these things you can just simulate in real time and see, and you can integrate real devices like energy meters and see what is the system performance or how the system is behaving. Nowadays, building energy management system is also coming, where with the help of online or wireless technologies and smart meter and smart appliances, you can control your appliances, when to turn on, when to turn off, and how these are gonna behave, and what happens to the system when these things happen. Because if people change their load or the utility change their load, so for example, if the utility pays you to turn on your washer in the time where the electric requirement is less, accordingly how will the electric power flow in an overall electric system changes can again be integrated with these communication protocol, and you can study home, even up to home level devices. So I have given you some insights, some research ideas, how real-time simulation typically works, and how it can be used for actually implementing our research algorithms. And these are not just limited to publications, and actually being used to test different things in real world applications. I'll just give a couple examples of real world. For example, if you see the National Renewable Energy Laboratory, they have a complete power hardware in loop simulation platforms, and multiple projects are being are currently running on power hardware in loop testings. And if you can go to NREL website, you can see all of these details. So what type of test they are doing? They are testing residential home based PV or energy. If people start to put more and more photovoltaic at their homes, what is going to happen to the system? They have tested solar PV integration on Hawaii grid. So Hawaii grid is a real grid, and they have tested what happens if more and more PV is integrated on a real grid with the help of power hardware in loop simulations. Different aspects of renewable or converter based sources that are coming. There are techniques like how you control the reactive power, or when to connect the system and to disconnect the system. Nowadays, people are talking about flexible loads. That means the utility can control your loads. So how these are being controlled, all of these things are typically being done in NREL at USA. Also, I would just like to show one real world example of ABB, where ABB uses a real-time simulator for their traction application. So how the train is going to perform, what power it's going to deliver, all of these things, and how the controller will behave in a real train. They are actually tested in real-time application, and they have shown in real testing that if you compare these results, the real-time data and their actual data from the train measurement, they actually sort of how much they are matching each other. So that's how they first test and then implement, and you can be sure that if your real-time performance is good, that means in a real world it's gonna work well. And then they are also testing the power management of a train. So typically that railway grid at many places work at a lower voltage. Typically we get 50 hertz or 60 hertz power supply, but the railway network typically operates at a lower voltage like 16.7 hertz. So the railway engine has to converts 50 hertz to 16.7 hertz, and that is there need to be these again power electronic converters that I just mentioned, AC to DC, DC to DC, all of these things, and these are also tested in real time simulation. And they have also discussed how they have done the partitioning. As I told, when you have big multiple things in the system, partitioning needs to be done to run the system at different cores, and that is being done, and they have done it. So basically, research labs, industries, all of them are using for different applications these real-time simulators and testing in real world. So uh, that's all from my side. I would like to conclude it with this way, that real-time simulation gives you the opportunity to save the time, integrate real devices or large power system, controller testing, prototype testing can be done, HIL or PHIL testing can be done. But the key points to keep in mind is you have to have proper selection of the devices that you use, the simulation techniques that you use, the time step that you use. All of those things should be used properly to get the desired results. If done right from inception of your idea to the final testing, all of these things can be done in a real-time simulator. And the applications are immense, as I told: large power system, renewable energy integration, control and protection, and many more, many more. So with this, I conclude. Before I go, I would just like to give a glimpse of there are so many industries who are making such simulators. Don't have any personal choice. They all have the same sort of behavior. But if you can read literatures like this, you will find the differences between them. For example, which manufacturer gives what type of hardware, what is their operating system, what are their capabilities, which protocol, communication protocol they can actually implement, and then for what applications you can use them, and any other thing which you need to take into view while doing your research using these systems. Just like these real-time hardwares, there are different power hardware in loop, as I told you. So you need power amplifiers. Again, you need to see what are the capabilities of those power amplifiers, and how which of these suits best your requirement, and then accordingly you can select whatever you need. And this is just not, this is just to give you an idea. This may not be 100% true, because this data is like 2017 published paper. So in 4 years, growth is immense, and this data may have changed, but this just to give you a glimpse that you can actually analyze what is required for your system, and then you can implement in your research. I would like to acknowledge IIT Delhi and Kansas State University, because few materials, few research, and few videos that I showed you are from my work at IIT Delhi and Kansas State Universities, and few research that I have done is, or few videos that I have shown you is based on these real-time simulators, Opal RTT, Space, and Typhoon. So acknowledgement is needed. That's all. Thank you. If you have any questions, any feedback, I'll be very happy to answer.
Thank you, sir, for providing really your unwavering commitment and such extensive detailing of your research work. Participants, please feel free to write your questions in the chat box if you have any query. Our speaker is there. We have one question in the chat box, that is that any limitation with simulator, and what type of challenges actually we faces with simulator?
Okay, so the answer of this question is gonna be a little bit generic, because it will depend on which device you use. There are so many, as I told at the end in one of the slides, there are so many manufacturers and industries available. All have different CPUs. So first, in simple terms, if I tell you, the thing is you have to see how many cores are there, because as the number of core increases, as the flexibility increases, you can do paralleling, you can do partitioning, and you can do all sort of stuffs. Then is it CPU based or FPGA based? That depends on the requirement, because if it is CPU based, it has a limitation. CPU based can go up to kilohertz sort of range, but if you have to go to nanohertz sort of Like even has that sampling range, then FPGA based is more required. And then what software integration is required? For example, OpenRT integrates with MATLAB, DSpace integrates with MATLAB, but Typhoon Hill has got its own software. So that type of thing you have to think based on your requirement. But as someone asked, what are the challenges? Challenges is just these, that well, they are costly. Again, you have to think on your requirement, and then you have to understand to make them work. If you do not use a correct sampling time, then can be overruns. As I told, in the case of overruns, you do not get the correct results. You may miss the real time approach. So those things you need to avoid.
Okay, thank you for answering the question. We have another question from Dr. Kirti. Is the simulator used is industrial grade in power engineering?
Yes. There are many examples. People are now using it industrial grade. I gave you the example of ABB, which they are using for their train applications, and they're converting 110 kV 50 hertz to 110 kV 16.7 hertz. All of that is actually simulated in there. So there is a paper from ABB, or sort of a white paper sort of thing, uh, which I showed you in my uh, slides. If you can just search on net, is need for speed real-time simulation for power electronics in railway applications and beyond. That's the title of it. So that's how, and if you just search applications, you'll see many of them in practical world.
Okay. So, HOD sir, any questions from HOD sir? Okay, meanwhile, I will get back there. I have seen one example in real world slide, which is anti-islanding evaluation.
Right.
So can you please throw some light on how the simulator will be used for such kind of real world application?
Okay, so first of all, we need to understand what is anti-islanding and islanding basically. So, for example, what happens? Let's say we have a solar photovoltaic or any sort of distributed generation like this, and then we connect it to the grid, right? So, let's say when there is a grid outage, in that case, let's say there is a intentional grid outage. That means there is some mechanic who need to do some work on the transmission line, or on the towers or somewhere, and they actually turn off the grid. And in that case, if they turn off the grid and they go there to do the work, and if your photovoltaic is still producing voltage, is still energizing the system, then there is a risk of shock and damage to life and components. So that is why there is an islanding requirement that says that if the grid is not there, you have to disconnect, or if the grid is beyond a certain level, if there is a over voltage, under voltage, over frequency, under frequency, in those scenarios you have to disconnect your distributed generator. At the same time, there is anti-island, which means that uh, if the system is within a range, then you have to remain there. If you disconnect suddenly, the grid will see a certain change. So when to connect, when to disconnect, when not to disconnect, all of these things come under the study of islanding and anti-islanding studies. And for that, you need to have a big system, and you have to integrate your distributed generation with that big system. So how can you do that? You make your big system in the real-time simulator and have a physical device and integrate it with through a power amplifier, or even you can just make the simulation. You can have the converter in the simulation, and then you can study those islanding or anti-islanding effects.
Okay. That was quite interesting and new for me as well, personally, because I'm from electronics domain, so I would was interested into that.
Yeah, I hope I could make some sense to people. I try to reduce that technical contents related to power or control, but still there were some which were needed. I just kept them only.
No, it was quite interesting to see a lot of simulators and how they are being applied in electrical domain, and the real world examples where you showed the actually video of the simulator. So that was quite interesting, and your the session was amazing. Means you have worked so hard and you have delivered it means consistently. So there was definitely an unwavering commitment on your side, which we'd really appreciate. I will request
Thank you.
HOD sir to conclude with some of your expert questions.
Really, I was watching. Thank you, Asta. Sir, Dr. Dushyant sir, I am really thankful to you. How nicely you have explained such a vast circuit of grid and simulation. Even if 10% of us we can simulate, I think we can complete a better research. What you have given. I have learned at least 20%. And I am very much thankful to you. Being electronics and communication person, power electronics, I could learn at least 20 to 30%. I can say I have learned from your speech. And
Thank you.
I will try to at least write one paper in this. I am very
Thank
much
you.
thankful to this. Thankful to you, sir. Very much thankful to you. Thanks a
I'm
lot.
glad. I'm glad. Thank you.
Okay, so now I would request Dr. Kirti ma'am to uh, present vote of thanks.
Okay. Good evening, one and all. I want to thank the Director GLBITM, Dr. Rajiv Agrawal sir, Head of Department, Dr. Stendra Sharma, and all the faculty members for attending this informative session. We would also very thankful towards our presenter, Dr. Dushyant Sharma. The session was quite informative and gave us a brief overview and covers basic to advanced level understanding on the applications of the power engineering subject. He also shares some new innovation trends in the area of simulation tools in electronics and communication engineering arena. I want to thank all the participants for sparing your valuable time. We look forward to connect with you, sir, for upcoming events also. Thank you. Thank you so much, everyone. Thank you so much.
Thank you, ma'am, for giving vote of thanks. So there's a quick announcement. Please, we have shared the attendance link with all. Based on that, the certificates will be distributed. So please be attentive in all these sessions. These are specially arranged for the participants, and we will be grateful, and the speaker will be encouraged with your active participation. So we will be meeting tomorrow at same time, that is 10 a.m. with the another speaker, which is in line, that is Dr. Brahmajit Singh. So thank you all, and thank you, sir, for today's session. We have really very much means I am very much delighted personally to see this session and learn so many simulators and all. And I do know that our department faculties, they were being there linked, I was seeing, and they are also being very interested. And I hope that we will be means we have a conference also, we are organizing such events frequently, so we will be having such more collaborations in near future from with you. So thank you all, thank you for
Thank you. Thank you for inviting me here. Thank you.
Thank you.
Thanks a lot.